Hi everyone, my name is Georgios Zacharopoulos. I'm a PhD student from Università of Lugano, and I'm here to present you our latest, one of our latest papers that was also presented in Impact 2017 in the HiPEC conference. So I'm here to talk about data reuse analysis and how this can be crucial for synthesizing custom instructions, or also called accelerators, in sliding window applications. Let me start with giving you a brief intro regarding performance, and by performance I mean energy efficiency and execution time. So what is the expectation on performance? We expect performance to keep increasing over time, and we have in one end Moore's law that suggests that the number of transistors doubles roughly every 18 months on the same area of the chip, and also on the other end Reynolds scaling, which states that the energy required is proportional to the size of the transistor. So as transistors get smaller and smaller, we can put more of them in the same area of the chip, and in the end the power is constant. But in reality it is not like that. So unfortunately performance is not increasing anymore, or at least it is not increasing as we would expect. And the reason for that is because we have reached what is called the breakdown of dynamic scaling. So we have reached some physical constraints, we experience current leakage now in our chips, and the era of free lunch is not here anymore. So we went from single cores to multiple cores, and this helped improve performance, especially for applications that could really exploit the parallelism, like graphics rendering, but we could not tackle the initial problem, which resulted eventually into the dark silicon issue, which means that we can only power up only certain parts of our chip at a given time if we do not want to exceed predefined power and thermal constraints. So if we do not want to result into overheating issues, we're going to have our chip is going to look more or less like that, like a building during the night where only a number of offices is illuminated. So what do? We shift from the homogeneous era to the heterogeneous computing era. So instead of having multiple instances of the same CPU, now we have specialized hardware into the game, such as GPUs, which can really help accelerating a certain kind of applications. So we have specialized hardware in order to treat applications in a more appropriate way, to cater for its needs and thus increase performance. Talking about specialized hardware, let's use this graphical aid to just see the trend here. So comparing a DSP, a domain-specific processor, to a general-purpose CPU, we can see that as the specialization increases, same goes for performance. Also, the same trend is seen in an AZIP, an application-specific instruction set processor, where it is even more specialized, and we can achieve even better performance for a certain kind of applications. In the far end, we have ASICs, which are hardwired pieces of hardware, specifically designed to execute a given application or a kernel. Okay, so the trend is like that. What we have been using for our research is a general-purpose CPU loosely coupled with hardware accelerators. Okay, so this sounds very simple. And then what do? We can just use very good accelerators and we can achieve performance. So it's like, okay, fine, trivial. Well, not exactly, because data transfer can be the bottleneck here. So it doesn't matter if we can have very efficient accelerators. If we do not have the data at the time that we need it in our accelerators, then we're not going to exploit the benefit that we're promising. That's why many researchers have looked into accelerating data transfer between accelerators and memory. Others investigated having custom storage as an optimization, practically using the same principles as having a cache. And what do we want is to try to identify this data reuse in certain applications and build custom storage for that, but more efficient custom storages. So some researchers have already looked into designing custom storage, but in their implementations they were relying too much on source-to-source transformations, and also in the final implementation they were having limited parallelism and large internal buffers, so making heavy use of the resources. What we want to achieve is a final implementation where we can have multiple parallel data paths, hardware data paths, and more area-efficient accelerators. Okay, let me give you an example of the data reuse we're talking about here. So this is an example of a Sobel benchmark, an edge detection image algorithm. Here we have two loops. Within the innermost body of the loop, there are 9 loads taking place from an image. We could visualize these accesses like that, like a window of loads, a window of accesses. And throughout the execution, we could visualize it like that, like having our iteration domain. And in every consecutive iteration, we could see something like that. So we can see that there is significant level of data reuse among consecutive iterations. In fact, 2/3 in this case. Not only that, but if you could also have not only one window of access, not only one data path, but 2 at the same time. So if you would enroll the external loop, there's even more data reuse potential there. And by combining those two, we can see that the data level reuse is quite significant. Okay, so this sounds great, but how can we really detect that? Well, what better way to do that than by using compilers? And that's exactly what we did. So first we perform source code analysis, and then we identify this data reuse potential in the sliding window applications by using, of course, LLVM and Polly, a big collection of polyhedral analysis passes. Okay, so what do? We developed our own LLVM-Polly analysis pass, and we were interested in identifying 3 very essential characteristics here: the window size, the stride, and the whole iteration domain, so the whole frame size within which the window is moving in. Okay, so to sum up, in every application, what do we get? We retrieve the following things: the horizontal and vertical window size, the stride, and the iteration domain. Let's see how we can use this to design our buffer. First thing first, input width. This is practically a parameter and an architectural constraint regarding the implementation. So as larger the input width is, the larger can be also the horizontal width of our buffer. This is equal to the horizontal width of the buffer. In this case, we have one more. So in this case, the input width is equal to 4. In the previous example, the horizontal width of the window was 3. So we can have now 2 parallel data paths, since the input width allows us to go a bit more. So in this case, the input width is equal to the horizontal window size plus 1. The vertical width of the buffer is always equal to the vertical window size. And in the end, we just concatenate the results from our execution when we store them back to main memory. Let's see how this buffer works in an example. Okay, so we have, in this case, 2 parallel data paths, since we had the input width would allow us to do so. And what do we do throughout every iteration is that we just discard the topmost row and we store only one new row. And we go on like that until we reach the limits of the vertical width of the whole iteration domain. And then we perform a horizontal displacement, which is equal to the input width that we had available minus the horizontal window size plus 1. In this case, since the horizontal window size since the input width was equal to the horizontal window size plus 1, the horizontal displacement is equal to 2. It can be more intuitively be seen as the displacement being equal to the number of data paths that we have available times the stride. So in this case, it's 2 times 1. All right, let's see now the experimental setup for that. So what are we comparing to? This was our approach. What is out there? What is the state of the art? So we're comparing against RoxyC and Vivaldi HLS, 2 widely used commercial tools for high-level synthesis. So what are the 3 features that we're most interested into targeting? First, pipelining data reuse, which I remind you is the data reuse among consecutive iterations. This is supported by RoxyC, supported by Vivaldi only after extensive manual rewrites of the code, and supported by our approach. Second, unrolling data reuse, which is the data reuse that can be exploited having parallel data paths. This is not supported by RoxyC, not supported by Vivaldi, and supported by our approach. Third, having the ability of parameterizing the input-output width. So practically being able to design a buffer that can cater for the architectural constraint needs, and the bigger, the better normally. But of course, more expensive area-wise. This is not supported by XCC, it is supported by Vivado HLS, and it is also supported by our approach. Okay, so moving on next, our final implementation target was an FPGA Xilinx Virtex 7. We considered three possible configurations. Each configuration depends on the input width available from the architectural constraint, which also affects the number of data paths that we're going to have in the end. So these are the benchmarks that we considered with the respective window sizes. First configuration would be the single data path one. Single data path means that the input width available is exactly the same as the width of the input width available is exactly equal to the window size, horizontal width, as you can see here. Multiple data path approach, where the input width available is larger, and so we can have even more data paths. And then an extra large version of that, a bigger extra multiple data path approach, XMDP, as we call it here, which can give us even larger input width and a lot more number of data paths. Okay, let's see those in play now. So regarding execution time, we can see that, just a first disclaimer, we have here Vivado no rewrite and Vivado rewrite. So the Vivado no rewrite means that we were using Vivado by default, because in order to have pipelining data reuse, we were needed to do, there was some manual effort required there to extensively rewrite the code. Okay, so we're executing a 100 by 100 frame here, and we can see that our approach, the single data path approach, was almost as good as the best competitor, Vivado rewrite in this case. The multiple data path approach was a lot better than the competition, and in fact the XMDP, the extra multiple data path approach, even better. In fact, it was, for example, for Sobel benchmark, it's an order of magnitude better than the best competitor, and 2 orders of magnitude better, almost 2 orders of magnitude better than the rest. Now let's see the area comparison. Okay, so regarding flip-flops, we can see that for the single data path approach, we're using a lot less than our competitors. For MDP and XMDP approaches, we're using in most cases, the same or slightly more. For lookup tables now, for the SDP approach, we use, again, more or less the same comparing to the best approach, but for MDP and XMDP approach, we use quite more, and this is expected since now we have more data paths, more logic required, more lookup tables required. Okay, so this is the overhead we had to pay before. Let's sum this up in one graph and comparing the two best approaches, the two best configurations that we have against the best competitor that is out there, Vivado rewrite in this case. So, MDP against Vivado rewrite. For example, for the Sobel benchmark, we can see that we have 5x, almost 5x speed up. And this is quite significant. For XMDP approach, it's even more than 12x, which is quite impressive. The speed up that we can achieve with this approach is quite impressive. Of course, there is some area overhead involved, but not that much. So for flip-flops, you can see that this is always more or less 1 or 2 times more, max. But for lookup tables, it's a bit more. So for Sobel benchmark, for example, it's a bit more than 2 times more for MDP approach, and a bit more than 4 times more for the XMDP approach, for the multiple data paths and the extra large multiple data path approach, which is, though, understandable. So to conclude, what do we do here? We try to make a data reuse analysis by using the LLVM-Polly /Polly framework in order to optimize high-level synthesis, so achieve better high-level synthesis for accelerators, targeting sliding window applications. So we used Polly to achieve better hardware designs here. What did we make happen here? So to exploit more, what was our target? To exploit more data locality, we had to design more efficient buffers in the end, to make better use of our resources, and of course, in the end, achieve much better performance. Thank you very much for your attention, and I'm waiting for your questions. I know.
So do we have any questions?
Thank you.
Could you give some intuition about the different benchmarks used? Like, what are they? And in particular, why? Why does the approach fail on some of the other benchmarks?
Yeah. So all of these benchmarks, you could see them as sliding window applications, right? Because they're all processing images in a given way. Sobel, Max Filter, and the last one was. So I have the slide here. Yeah. And SAD. Now it's all about practically having a big image, or a big or larger, whatever the input can really vary, and just processing an image. And you know, statically, you can have statically this kind of information. You know what is the pattern. Like now I'm taking this 9 inputs, 9 pixels, then another 9 one, and so on. So since you can have statically this kind of information, why not try to exploit it by automating the whole methodology and feeding this kind of information to the synthesis tool? And this is what we try to do. Thank you.
So we probably have time for 1 or 2 more questions. Someone
There.
right in the back.
So, maybe a question.
Yeah.
Do you only use analysis or also transformation capabilities? So
No, no.
do you auto-generate the new code, or do you only analyze and then have some custom generation passes?
Yeah, no, I'm only analyzing, so I'm the compiler guy of the group.
Okay.
The others are more like the synthesis hardware guys that don't really know much about that. So no, I'm just performing the analysis, at least for this kind of work. I was only practically performing the analysis automatically for each benchmark, and I was feeding it directly to them in their own synthesis tool in order to do that. Then, of course, the synthesis tool, depending on what it can be, it can also be kind of scripted and try to automate the whole process. Thank you.
Sure.
Does any of the tools also support using multiplication units on the FPGAs? And if yes, do you see different load changes on that compared to the number of flip-flops or lookup tables?
If they I'm sorry, your question was if they support multiplication units.
Correct.
Yeah, well, to be honest, I'm not really familiar with all the kind of like, if they do support that, but from my, experience, well, the synthesis tool, the synthesis part is more the work of my colleagues, so they would know more about these kind of details. I would expect that since they are state of the art, they do support this, but they have certain limitations. So in most cases in the synthesis part, you have to specify manually what you want to do. That's it. I can provide this information automatically by using the compiler. Thank you.
Okay, that's probably the last question.
Thank you. Thank you again for your attention.